Now we will start the second lecture of week 6 of this course. In this lecture, I will be talking about the notations. Okay, so the notations for the various crystal classes. Okay, so in the last lecture you learnt all the crystal classes. Now I will talk about the notations that are used, and I will briefly mention the Schoenflies notation, okay, which is more common for molecular point groups, but I will focus on the Herrmann notation or the international symbols. So week 6 lecture 2 will be notation for the 32 crystal classes, and I will be focusing only on the crystal classes. We will go to the space groups little in the next lecture, but we will focus on in this lecture on the crystal classes. Okay. So there are two common notations that are used. One is called the Schoenflies notation and the other is the Herrmann notation. And you should keep in mind that the crystallographic classes are essentially similar to molecular point groups. Okay. These are like molecular point groups for objects for the outer shape of the crystal. And conventionally, molecular point groups use rotoreflections instead of rotoinversions. So in crystals we use rotoinversions, whereas in molecular point groups rotoreflections are used. Now the Schoenflies notation you might have seen in molecular group theory. Okay, so there are terms like C3V, D4H, OH for octahedral, TD for tetrahedral, and so on. The Herrmann notation, this is something you might not be so familiar with, but in this the names of the point groups are just like numbers like 4, 4m, 4mm, or 4 bar 2m, etc. So typically up to three numbers, and we will see what kind of combinations are there. Okay. So now in order to understand the Herrmann notation, and in particular the Herrmann notation, we need a concept called unique operations. Okay. The idea is that if you look at the total number of symmetry operations, so I will just step back a little bit. So for example, the octahedral point group, okay, now you know that it has a very large number of operations, it has 48 operations, okay, and that indicates the presence of all these 48 operations. Now it turns out that not all these 48 are unique, okay, some of them are not unique, okay, some of them are implied by the existence of others. Okay. So the concept of a unique operation can be understood in the following way. So suppose you have an n-fold rotation axis and an axis perpendicular to it, another rotation axis that is perpendicular to it. Okay. So you could have something like this. You have a let us say there is a C3, if you have a C3 axis, and let us say you have in the plane perpendicular to it you have a, let us say, a C2. So the C2 is perpendicular to the C3. Okay. Now this automatically implies, so having a C3 automatically implies that you should have two more C2s. Okay. So there will be two more C2 axes which are basically 120 degrees from rather it will be you will have two more C2 axes that will be oriented like this and like this. Okay. So these are again these are perpendicular to the plane of the paper. Okay. So basically this implies two more C2 axes. Okay. So in a sense one of these C2 axes is unique, the other two are implied by the presence of this perpendicular C3. So this gives you an idea of where the concept of unique axis comes. Similarly, if you had a let me look at this screen. If you had a mirror plane and you had a C3 axis, let us say perpendicular to this mirror. So this is a C3 that is perpendicular to this that contains the mirror, and it is perpendicular to the screen. So this is a mirror plane. Okay, I am showing it by dashed. Okay, but it is perpendicular to the screen of the paper, perpendicular to the screen. And now if you have a C3 axis, so the C3 axis is actually coming out of the screen of the paper. So this C3 axis is actually coming out of the screen. Okay, and now so the C3 axis is perpendicular and it contains this mirror. So the mirror, the C3 axis lies in the mirror. Okay, and what this implies is that it automatically implies that there should be two more C3 axes or two more mirrors. It indicates that there should be two more mirrors, and I will show them. There will be one this way and one in this direction. Okay, so it automatically indicates that there should be two more mirrors. So the point is that one of these mirrors is unique, the other two are implied, okay, by the existence of C3 and the first mirror. In other words, a unique operation is an operation that is not produced by other symmetry operations. So you can think of one of these mirrors as produced by this mirror followed by a C3. A combination of C3 operated on one mirror will give you another mirror. So a unique operation is one that is not produced by other operations. Okay, so this is a way to, this concept of unique operations will be essential in describing the symmetries or in identifying the Herrmann-Morgan notations. Now one of the very important features of this Herrmann-Morgan notation, okay, and I'll emphasize this. Okay, so Herrmann-Morgan notations are very terse. Okay, I am using the word terse. Terse basically means they are very brief. Okay, the terse means very brief. Okay, so they are very compact notations. Okay, they are very compact notations, and essentially through these very compact notations, you are showing the entire set of symmetry operations of a point group. Okay, now so coming to the Herrmann-Morgan international symbols. Okay, so this is a procedure for identifying the Herrmann-Morgan international symbols. So what you do is first you identify all the unique rotation or roto inversion axis and denote them either by n or n bar. So identify all the unique roto inversion axis and denote each of them by the letter n or n bar. Okay, if it is a roto inversion, you will use n bar. If it is a, for example, if you have a three-fold roto inversion, you will use 3 bar. Okay, if you have a 4-fold rotation, you will just use 4. Okay, so you identify all. Okay, the important word is all the unique rotation or roto inversion axis and denote them by n or n bar, and you can show that you cannot have more than 3 of such unique rotation and roto inversion axis. So you can get maximum 3 of these numbers. Next, what you do is you identify all unique mirrors and denote them by m. Okay, so you see how many mirrors, these are mirror reflections. Okay, so how many mirror reflections, mirror planes are there? Identify all of them and look at which ones are unique, and you denote them by this letter m. Okay, so these are the first 2 steps, and again you can show that you cannot have more than 3 unique mirrors, okay, in a 3-dimensional crystal. Now if a mirror is perpendicular to some rotation axis, then you denote it as n by m. So, if m is a mirror that is perpendicular to a rotation axis n, then you denote the axis and you put a slash between the axis and the mirror symbol. So, you denote it as n by m. Similarly, if it is perpendicular to a roto inversion axis n bar, then you denote it as n bar by m. Okay. And just these three operations, it gives the long form of the crystallographic class. And in this lecture, I will focus on the long form of the Herrmann international symbols. Okay, that gives you the crystallographic class. So that is all you need to do, and as we said, crystallographic class only refers to rotation and reflection. Now you might ask, what about the inversion center? Now the inversion center is nothing but 1 bar. Okay, so we keep in mind that inversion is equivalent to 1 bar. Okay, so it is included in 1 bar. Okay, and so this essentially you are taking care of all the symmetry elements of this crystal, okay, of the point group of the crystal. Okay, so now let us look at some examples. Okay, we will take some very simple examples that will tell you how to do this. So first let me take a rectangular block. Okay, and I will just show it like this. So you have something like this. Perfect rectangular block. Okay, so now let's write the Herrmann symbol for the point group of this block. Okay, so the first step is to identify all the symmetry axes. Now this rectangular block has all sides different. Okay, so the only rotations that are there are essentially there's a two-fold axis of rotation this way. So two-fold axis of rotation, then there is a two-fold axis of rotation that goes this way. And another two-fold axis of rotation that goes in this direction. Okay. So there are three two-fold axis of rotation. So we will write 2, 2, 2. Okay. Now, are there any other rotation axis in this rectangular block? No, there is no other rotation axis in this rectangular block. What about the mirrors? What about the mirror planes? Now again you can see that I'll just show it by a dotted line that intersects. So if you imagine that there is a mirror that goes this way, this would be a mirror plane. Okay, so it contains this axis, okay, and this axis. So it is a plane containing this axis and this axis. Okay, so you have a mirror, and similarly you can have two more mirrors. Okay, those that contain one that will look like this. Okay, and a third one that will be perpendicular to this. Okay, so those will be the three mirror axes. So three mirror planes. So you have three mirror planes, and notice that each of these mirrors is perpendicular to one of the axes. So for example, if you take let me shade it in light green. So if you take this mirror, that is perpendicular to this axis. Okay. So, this mirror is perpendicular to this C2 axis, and similarly the other two mirrors are also perpendicular to the axis. So, we can just put a dash between this. You can write it as 2 by m, or if you are writing in a single sentence you can just write it as 2/m. Okay. So, this is really the point group. So, the point group of this rectangular block is 2 by m, 2 by m, 2 by m. Okay. You can write it as, if you are writing in a single sentence, you can write it as 2 by m, 2 by m, 2 by m. Okay. Okay. This is the point group of this rectangular block. Okay. Next, let us consider something that is slightly different. Okay. Let us take something that is again it is rectangular, but it is but there are one of the sides is a square. Okay. So, if you have something like this, and this side is a square, okay. Now, what you have is you have now this axis of rotation becomes a four-fold axis, okay, and the other two-fold axis remain as they are. So, these two continue to be two-fold axis. Okay. So, these two continue to be two-fold axis, but you have a four-fold axis. So, this is a two-fold axis, this is a two-fold axis. Now, what about the mirrors? Okay. So, we definitely have one mirror that is perpendicular to this four-fold axis. Okay. So, we have one mirror that is perpendicular to this four-fold axis, and I will show it in this way. Okay. So, let me write. So, you have a 4, you have a 2, and you have a 2. Okay. And we definitely have a mirror that is perpendicular to this four-fold axis. So, then I will have a 4, let me put a slash and an m. Now, again, now you actually have the mirrors containing this. I will show them here. Okay. These are, so you have a mirror that is perpendicular to the 2 axis, to this 2 axis. So, you have this mirror. Okay. You have another mirror that contains the other . Okay, that is perpendicular to this 2 axis. So this mirror is perpendicular to this 2 axis, and this mirror is perpendicular to this 2 axis. Okay. But there are two other mirrors. And I will just show the one will be this way. And one will be in this direction. I will not show the full mirror. Okay. So, actually you have a total of, you have 4 plus 1, 5 mirrors, 5 mirrors. Okay. But you can easily see that you have a mirror perpendicular to this 2 and a mirror perpendicular to this 2. Okay. And because of this four-fold symmetry, okay, this one mirror automatically implies 3 additional mirrors. Okay. So, what I mean to say is that not all of these are unique, and we just write the mirrors that are perpendicular to these. Okay. So, out of these 5 mirrors, okay, we write only 3 of them, and in fact actually truly only 2 of them are unique, but since you also have one that is perpendicular to this 2, we write that also. Okay. So, the space group now is 4 by m, 2 by m, 2 by m. Okay. Now, the third example I am going to do is that of a cube. Okay. Slightly we will just make it a little more complicated than a regular cube. Okay. So, we imagine that you have a cube, but now we assume that these C3, you do not have C3 axis, but you have 3 bar axis. This is a 3 bar axis. So, you have 4, instead of having 4 3 axis, 3-fold axis, you have 4 3 bar axis. So, this is not a perfect cube. You imagine that there is something that makes this, that converts this 3 axis into a 3 bar axis. Okay. So, you have 4 3 axis, 4 3 bar axis. Okay. And now you can write. So, you still have the 4-fold axis. Okay. So, the 4-fold axis is still there as it is. So, you have this, and so you have 3 4-fold axis. Okay. So, this is a 4, 4 and a 4. Now, notice that out of these there is only one unique axis here. Okay. So because you have a 4-fold axis, okay, if you have one axis of rotation, then this is the second one is automatically implied. So if you take this 4 axis, okay, and this 4 axis, then it automatically implies this 4. Actually, it implies 2 other 4-fold axis, which we are not showing here. Okay, it also implies 2 other 4-fold axis. Okay, but there are additional axis that are there. Okay, and that is this 2-fold axis. So, for example, you have one 2-fold axis like this. Okay, coming from going through the center of one face and coming out on the other side. Okay, so you have these 2-fold axis. Okay, and again you have a total of 6 of these 2-fold axis. Okay, but again only one of them is unique. Okay, because of all these 4-fold axis. Okay, so you have a 4, you have a 3 bar, and you have a 2. Okay, so this is a 2-fold axis. So this, let me use a slightly different color just for the 2-fold axis. So this is a 2-fold axis, this is another 2-fold axis, and there are a total of 12 of them 2-fold axis. So actually you have if you look at the total number of operations, you have 3 4-fold axis, you have 6 2-fold axis, and you have 4 3 bar axis. Okay. However, you can easily show that only one of these 3 bars is unique and only one of these 2's is unique. Okay. And now if you take the total number of mirrors, you have a total of 9 mirrors. Okay. And again this is not very hard to show. You have 9 mirrors. Okay. And the mirrors are actually perpendicular to the 4 axis and the 2 axis. There is no mirror perpendicular to the 3 bar roto inversion axis. Okay. So you can put slashes here, put the mirrors, and this is the space group symbol. So now you have the space group symbol for this cube that has a 3 bar instead of a perfect 3-fold rotation. This is slightly, you can think of this as some sort of unsymmetrical cube. Okay. Now if you had a perfect cube, okay, then you can easily see that it will be 4 by m, 3, 3, 3, 2 by m. Okay. So the long form for the perfect cube will be 4 by m, 3, 2 by m. Okay. So now with this with these examples we will just list all the notations for all the crystal classes, and we again we will start with the most unsymmetrical. So the most unsymmetrical is the triclinic system. Okay, it is called the PDL class, and there is just a 1. Okay, so the only there is 1 is just the identity, there is no symmetry operation. So the class notation is just 1. Okay, so this is the Herrmann symbol. Okay, the Schoenflies symbol for this is C1. The second is the pinacoidal, where it is 1 bar is the only symmetry. So it has a center of inversion. Okay, so you just denote it by 1 bar. In the Schoenflies notation, you either use Ci or you use S2. Ci is equivalent to S2. Similarly, the sphenoidal has only a two-fold axis, so this would be a C2 group in the Schoenflies. So these are the Schoenflies symbols. Schoenflies notation. Similarly, the monocline, if you just have a mirror, okay, then the Herrmann symbol is just M for the space group. Here this is actually denoted as CS or C1H. Okay, so H reflects the fact that you have a mirror plane. Okay. Now what about 2 by m? 2 by m, okay, 2 by m. Now the Herrmann notation, okay, so we said that 2 by m automatically implies an inversion center. The Herrmann notation is just 2 by m. Okay, and again the inversion center is not necessary, because for the Herrmann notation, in the Schoenflies symbol you will write this as C2H. Okay. Now what about the orthorhombic group? So the 2 to 2, okay, so you can have a Herrmann notation 2 to 2. The Schoenflies symbol is D2. Okay, the MM2 would be C2V. I'll just note this, and then this is D2H. Okay. Again, so you see that the existence of the mirror, these are the symbol 2 is used, C2 or D2 implies a two-fold axis of rotation, and then there are various symbols to indicate the directions of the mirrors, of the mirror planes. Okay. Now again we won't be talking too much about the Schoenflies notation, but it's but it is likely that you will see it in some cases. Okay. Now let's go to the groups, to the tetragonal groups. Okay. Now if you just have a 4-fold axis, then the Schoenflies notation is C4. If you have a 4 bar, then the Schoenflies notation is S4. Then you have a 4 by m, then it is C4H. If you have a 4 to 2, okay, now the Schoenflies symbol is just D4. Okay. Similarly, if you have 4 mm, this is C4V. Okay. The 4 bar 2m, this is D2D, and then the 4 by m, 2 by m, 2 by m, this is denoted as D4H. Okay, so these are the tetragonal groups. Now I won't list all the trigonal hexagonal. Okay, I'll just say that this is C3. This is actually C3 and I. This is an S6. Okay, and then this you have D3. You have D3D. This is 3m corresponds to C3V. this is D3D, 6 is just C6, S, this 6 bar is actually denoted as C3H, and 6 by M is denoted as C6H. Okay. This is 622 is denoted as D6. Okay. Again, I do not expect you to know all these. However, you can tell by looking at the symbol that you have a 3-fold axis or a 6-fold axis. And so let me just list the last one. This one, okay, is called D6H. Okay, and I mean we can just complete the set. So the 6 bar M2 is denoted as D3H, and 6 bar MM is denoted as C6V. Okay, so these are the Schoenflies notation. Now I mean if you are familiar with molecular group theory, you will recognize that V stands for a vertical mirror, H stands for horizontal mirror, and D stands for diagonal mirrors. Okay, but again I am not going to emphasize all these names. Okay, so I won't expect you to know all the Schoenflies symbols, nor would I expect you to know all the names of these crystal classes. So other than the most symmetric or the least symmetric, I won't expect you to remember all these names. And let us complete it. So the cubic class is 2, 3. Okay, 2, 3 is the Herrmann-Mauguin notation. In this is tetraloidal, the symbol is just a T. Okay, so and then this is TH, this is O, TD, and this is OH. Okay, so the 48 operations, the group which is 4 by M, 3 bar, 2 by M, 2 by M. This is the octahedral point group. Okay, so you can look at all these point group symbols. Okay, and in some sense there is a logic in all of them. Okay, definitely the Herrmann-Mauguin notations can be derived for the most part. Okay, there are some conventions that are used, but for the most part you can derive them. The Schoenflies symbols, yes, there are some conventions there also, and you can understand these conventions based on the symmetry operations in the point group. Okay. So next we will extend this discussion. Okay, we'll talk about a more truncated form of this Herrmann-Mauguin notation called the short form, and then we'll extend the discussion to space groups. Thank you.